Okay, guys, in chapter 15, section number 1, this is the main idea here that we will going through. The first thing is the hydronium ion and the hydroxide ion, the pH scale, the calculations of involving the pH. The first things we need to recall the thing that we studied about the solutions, if you remember from the previous year. The things that happen to the covalent compound is called the ionizations. In today's sections, we will see the self-ionizations of the water. So let's see that happening here in the whiteboard or the black one. It's better. Okay. So the first main idea here in the book, self-ionization of water. From the name, ionizations mean that the molecules will separate to forming what? To forming what, Ahmed? Ions. To forming what? Ions. We need to explain how that happened. So simply, if you look here, a water molecules, H2O, have a neighbor water molecules, HOH, the same thing, right? Okay? With the reversible reactions in an equilibrium state. Do you remember the equilibriums? Or the reactions of the equilibrium that have in two directions, right? Forward and backward reactions. This is well forming a hydronium ion, H3O positive, plus OH negative. Okay? So we need to explain how this happened and then study the concentration of a hydronium to calculate it, okay? Again, how that happened? If you remember, the water molecule is a covalent compound, right? What meaning of a covalent compound? It consists of an oxygen atom attached to two hydrogen atoms. And this is molecules here, is a polar molecules. This is the 3D model molecules, and here is how the covalent bond molecules are present, okay? So the water molecule is a polar. What's mean of the polarity? It's mean that an even distribution of the electron. We have here oxygen atom, high electronegativity. So it's pull the electron of the covalent bond toward this, as this is increase the negativity, electronegativity of the atom, forming a partial negative charge upon the oxygen atom, a partial positive charge upon the hydrogen atom. The same thing here, a partial negative charge, and here a partial positive charge. Okay? So what happened here in the reactions here, it's very simple what happened. The hydrogen atom here separate, forming a proton, H positive. And this proton is transferring to this water molecule attached to it to forming a hydrogen ion. The question here, why this happened, if you look to the polarity of the molecules and imagine that this molecule here is separating the hydrogen, the proton here, and this proton is a positively charged near to another electrostatic charge negative. So positive charge near to a negative charge, what happened? Attract to each other, right? The opposite charge attract to each other, and the similar charge repel from each other, right? So the attraction having forming an hydronium ion. Okay? So the main idea is called self-ionization of water. We need to know how many molecules of hydronium produced from the ionization of water. For each 10 million molecules, how much produce? How much? Could you imagine? Could you imagine? Very good, Yataha. It's producing one hydronium ion. One hydronium ion. Okay? So if we write it in a language of the concentration, if you remember, this bracket here represents the concentration, right? Of a hydronium ion, H3O positive. By the way, you could just write it H positive. The same thing. Okay? Is equally add to 1/10 million. So could we convert it to an exponential? to become 1 times? Anyone? 10 to the power negative 7. And this is the concentration of the hydronium ion. And we know that the water molecule is a neutral compound, right? Right? So we call this hydronium ion, and what we call this? Hydroxide ion. It's a negatively charged. So if the water is neutral, this is mean they have equal concentration, right? So the concentration here of a hydroxide ion, OH negative, will be equal to what? Will be equal to what, guys? 1 times 10 to the power negative 7. Why? Because when the water molecule here separate to forming a hydronium ion, what is the rest of the molecule here? OH negative, and also with the same concentration, 10 to the power negative 7. Okay? Easy? Till now. Any questions? Omar, any questions? Okay. So, we know and understanding the molar concentration of a hydronium ion, but we need to know the equilibrium constant of that reactions. We will write it again, or we could just, okay, let's write it here. This is a back knowledge, guys, if you remember. If you remember when we studied the equilibrium in the previous year, we said that any K, a constant equilibrium, is equal to product over what? Reactant, okay? But we don't write the concentration of the solid substances and the liquid water. Why in this equation? Because it's have a constant concentration whenever the quantity change or not. For example, if I told you that you have a chocolate bar, okay, and you have the first bite of the chocolate bar, the same sweetness by the completing the whole bar or not, have the same sweetness, right? Or you're eating the first bite and you have the second one have a different concentrations of the sweetness? Nothing. So it's have a constant concentration. That's why it's equal, considered equal to 1. Let's prove that, and this is equilibrium here. For the ionization of water is called the W, okay, KW, self-ionization constant of the water, okay? So equal product of a reactant. What we have here in the product, the concentration of a hydronium ion as a product times the concentration of a hydroxide ion, right? Over the reactant. But if you look to the reactant, what we have here, what we have here, a liquid water. So we don't included that in the equation because the water have a constant concentration within their quantity change or not. So consider as a constant, as a solid substances, as the example of the chocolate that I gave it to you. Okay? Easy? So now we understand from where this comes, right? So we need to know the value of the KW is equal. If the hydronium ion, guys, we calculated 10 to the power negative 1 times 10 to the power negative 7, right? Times the concentration of a hydroxide one also times 10 to the power negative 7. So the KW will be always equal to what? 10 to the power negative 14. Okay? And this is a constant number. But remember, this is happened at, this is very important, at 25 degrees Celsius. Because the concentration, guys, is affected by the temperature. There is a directly proportional relation between the temperature directly proportional to the concentration. Okay? So increasing the temperatures would increase the concentration. So we consider this as an ideal calculations for it. The KW is always equal to negative 14. The question here, could we classify the type of the solution according to the concentration of the hydronium and hydroxide? Yes, it's very simple. If the substance is equal concentration, if the substance is neutral, okay, have equal concentration of hydronium, equal concentration of hydroxide. What happened? and this is multiplication always be equal to the same number, right? This is mean the increase of one of these ion will have a decrease in the other, right? So if we have, they are neutral solution. But if I have a solution have higher concentration of a hydronium, this is solution considered to be acidic or basic. A higher concentration of a hydronium, so consider as acidic, okay? But if the hydroxide ion is greater than the hydronium, so this is solution considered to be basic. So let's see that here, okay? Do you write this down, guys? Okay? We will back to it. So, do you see, guys? It calculated at 25 degrees Celsius. Because if you look here, if we change the temperature, increasing the temperatures will increase the value of the Kw. So we need to consider that in calculations. Here, the classifications of the substance types of solution according to the concentrations of the hydronium. So we have here 3 classifications. We have acidic solution. We have basic, neutral first. And we have basic solutions. So if we make a mathematical, here we always have here a hydronium concentration, a hydronium concentration, a hydronium concentration. This is a problem to write it like this. It is the same thing, guys, okay? We understand that H positive, it's mean hydronium, okay? And always we have the hydroxide ion near to it, the other face of the coin, okay? Okay, my question here, if the solution is acidic, so which is one is greater than another? Yusuf, Badawi. If the solution is acidic, this is mean the hydronium is greater than the hydroxide or the opposite? Exactly. Hydronium is greater than the hydroxide ion. If it's in neutral, if it's in neutral, this is mean what? Hydronium ion is equal or less or greater? Equal. And if it's basic, Muhammad, less than the hydroxide ion. This would mean the hydroxide ion will be greater. Okay? We need to prove that as a chemical calculations of the concentrations of the hydronium ion and hydroxide ion in different compounds. Okay? My question here, you have to note that. I want to ask you, the higher the concentration of a hydronium ion, increase the acidity or decrease it? Increase the acidity. So the lower the concentration of hydronium, decrease the acidity of the substances, right? Normally, when you're dealing with the acidity, guys, use one of the concentration as a scale for you. Don't confuse yourself by sometimes using hydronium ion and sometimes using hydroxide ion. Choose one of them and make all of your calculations in one of them. Because if I know one of them, could I get the other one? Yes, of course, because the Kw always be a constant number equal to what? Equal to what? 10 power negative 14, and this is what we gonna do. So, if we have an example of an basic, if you open the book page, see me in the book. If you open the book for the section 1, guys, you will find this. The self-ionization, it gives an example of a strong electrolyte. What am I meaning by a strong electrolyte? Page number 34 for the new edition, okay? It gives us an example of an NaOH as a strong electrolyte. Here, 34, okay? Page number 34 for the old edition of the book. It's page number, okay. No, here. 481. 481. The example here, give it to you NaOH. is an ionic compound, right? We make dissociation, okay? And this is NaOH is a strong electrolyte. What meaning by strong electrolyte? It's partially ionized or dissociate or completely ionized as it's strong. So what I'm meaning of a strong electrolyte from the previous year is completely ionized. What this mean? This mean all the ions here will have a one direction converted to an ions, okay? Forming an Na positive plus OH negative. The question here, he asks you to calculate the concentration of a hydronium ion. Any ideas how to calculate it? Okay. First, you have to write the equation. NaOH, yield. Of course, in the presence of water molecules, guys, okay? In the presence of water, because this is a solid substances, I dissolve it in water and make a solution of it. So this is when it's dissolved, given an Na positive plus OH negative. If I have 1 mole of it, at the coefficient here there is no exist, it's balance, it's 1. Produce how much of sodium? 1 mole also. And how much of hydroxide? 1 mole. So in the book, he gave you the concentration of the NaOH. How much? 1 times 10 to the power negative? Negative what? 2? Show me. Here. 1 times 10 to the power negative 2. So, if I am ionizing, 1 mole of NaOH have a concentration of 1 times 10 to the power negative 2. This is mean the 1 mole produce 1 mole of sodium, 1 times 10 to the power negative 2. And also 1 mole of hydroxide, 1 times 10 to the power negative 2. And this is what I need. The concentration of a hydroxide ion. Because if I have the concentration of a hydroxide, could I calculate the concentration of hydronium? It's very simple. If we go back here, guys, I have here the concentration of a hydroxide with me. And this is the constant number 10 to the power negative 14. Could I calculate this? Yes, very simple. Like this, Kw is equal to the concentration of a hydronium times the concentration of a hydroxide ion. I have that here, I have it from the equation, and I have this as a constant 10 to the power negative 14. So simply the concentration of a hydronium ion is equal to the Kw over the concentration of a hydroxide that I get it from the equation is equal 10 to the power negative 14 over 10 to the power negative 2 is equal 10 to the power negative 12, and this is considered as a strong base. Right? The lower the concentration of a hydronium, the lower the acidity and higher the basic solutions. Okay? Again, this is very important. I need you to understand it because we will simulate this to an acid solutions. Again, remember guys, for example, normally he will give you the concentration of the compound before you dissociate it. If I have 1 mole, and here, for example, I have 2 mole, so I have to multiply the concentration here by 2, okay? But here, the coefficient here, you find it 1, 1, 1, okay? But if I have here, for example, a coefficient of 2 hydroxide, I have to multiply this number by 2. But as I found 1, so I multiplied by 1, okay? Let's make the same thing to calculate the hydroxide ion from a hydronium ion, okay? Easy? So this gives us a hydronium ion, of course in excess of water, okay, don't forget that, plus the chloride ion, okay? Walid, help me. So here I have 1 mole, right? Produce how much? How much of hydronium? 1 mole. And how much of chlorine? Also 1 mole. The given concentration in the molarity of the HCl in the book, yeah, Ziad, how much? Ziad, is it exists down there, here, HCl, yes, hydrochloric acid here. Huh. 2 times 2 times 2 times 10 to the power negative 4. If the concentration and molarity is this value, so the 1 mole of hydronium have a concentration of what? 2 times 10 to the power negative 4 also, and the chlorine 2 times 10 to the power negative 4. The important for me what? The concentration of the hydronium, right? So if I have the concentration of the hydronium, could I get the hydroxide concentration? Yes, very simple. The Kw, self-ionization constant of water, is equal to the concentration of the hydronium ion times the concentration of the hydroxide ion. In this equation here, I have this as a constant, 1 times 10 to the power negative 14. I have this from the equation, so I could calculate this simply. I will say that the concentration of the hydroxide ion is equal to the ionization constant of the water over the concentration of the hydronium ion from the equation of the dissociation or ionization. So it's equal, Omar, 1 times 10 to the power negative 14. Speak louder, please. Negative 14 over 2 times 10 to the power negative 4. And this is what gives us 5, 1 over 2, 0.5, negative 4, so negative 10, and the decimal, so 5 times 10 to the power negative 11. Right? And this is considered as what? Remember, I told you this is point. What this here? Concentration of hydroxide, right? It's different from the concentration of hydronium. So if I wanted to determine the type of the solution here, look to the one of them, and I told you that follow only the hydronium ion, okay? And then when we come to the pH calculations, we will also follow the pH. So if the concentration here 2 times in negative 4, and we said that in the beginning, increasing the concentration of the hydronium ion, what this happened to the acidity? Acidity will increase. This is here, consider the hydrochloric acid as a strong acid. And this is the common name for it, stomach acid. It exists in your stomach, helping in the digestion process. Okay? Give me the book, please. Would you please solve the practice, page number 35, with the same idea, guys. Nothing different. Same idea. Page number 35. But before that, above the sample problem A, there is like a small paragraph. Okay, I want you to read it. Hamad, would you please read it? Page number 35. Okay, and above sample problem B. Yeah, I'm coming for you, don't worry. Page number 482 for the old edition, 35 for the new edition. Okay? Read, Ya Muhammad. Louder, please. The important line here, decreasing the concentration of one half, increasing the another. Okay? To be balanced, and this is what happened. Increasing the hydronium, decreasing the hydroxide. Then decreasing the hydroxide, decreasing the hydronium, and the equality mean the neutral. And this is considered to controlling the acidity or the basicity of the substances. Okay? So that's it for today. If you have questions, solve the practice. Go ahead and solve the practice. We have like 5 minutes. Solve the practice and show me your answer. Anyone have a questions? Anyone have a questions? Okay. Thank you all. Let me just stop recording.